All right, we are going to talk about several tools, several theorems or observations that we can use in factoring polynomials. Okay, so the first tool that we have is called the remainder theorem. And the first few are a little bit, well, we'll see what they are. The remainder theorem, if a polynomial f of x is divided by x minus k, so linear factor here, then the remainder is the value f of k. Honestly, this is a little bit surprising. There is a short little proof in your book. I'm not going to go through it here. If you want to, you can look. But let's look at how we'd use this. So use the remainder theorem to evaluate this polynomial at x equals 2. Okay, what this tells us is if we divide this polynomial by x minus 2, that's the same thing as just evaluating f of 2. So what that means is, let's divide this polynomial by the linear term x minus 2. We can use long division. We can use synthetic division. So you could practice doing synthetic division if you want. Make sure this is what you get. Okay, we use synthetic division. Bring down the 6. Multiply, add, multiply, add, multiply, add, multiply, add, and we get a remainder of 25. That tells us that f of 2 equals 25. This is honestly a little bit surprising to me. I wouldn't guess this was the case, but it is. And we can verify that by just evaluating f of 2, right? We can just put 2 into this polynomial, and sure enough, out comes 25. Oh, sorry, that keeps popping up. So this is a little bit of a novelty, to be honest, but it works. It's kind of an interesting little theorem. All right, here's another one, the factor theorem. This is probably pretty intuitive to you. If k is a 0 of f of x, k is a 0 if and only if k minus x is a factor of f of x. Okay, we've been using this for a long time with quadratics. You've been using this for a long time with quadratics. If you factor a quadratic and you get that it equals x minus 2 times x plus 3, then you know that 2 and negative 3 are zeros of that quadratic. That's all this is saying. Okay, so let's see. Here's an example where we'd use this. Show that x plus 2 is a factor of this cubic polynomial. And then find the remaining factors. Use the factors to determine the zeros of the polynomial. Okay, what this is asking is, this is saying factor this polynomial. That's what it's saying. And they're giving you one of the factors. Okay, what would you do if you had a composite number like 120, and we said, you know that 10 is a factor, find the remaining factors? What would you do? Well, you divide 120 by 10 and say, well, I'm left with 12. And then you'd factor that, what you had left, right? That's exactly what we're going to do, except it's going to be with polynomials. So we are going to divide this polynomial by x plus 2. It's a linear factor, so we can use synthetic division. So we're going to divide this cubic by this quadratic, or by this linear function. And sure enough, we do the synthetic division and we get a remainder of 0. That's what we'd expect if this is a factor, right? We would expect that we'd get a remainder of 0. So now we can write this polynomial, this cubic, as x plus 2 times this quadratic, where these coefficients are of the quadratic, right? X squared minus 8x plus 15. So now we have a linear function times a quadratic. Once we get it to a quadratic, we're in business. We know how to solve every single quadratic, right? We can factor it. We could complete the square if we wanted. We can always use the quadratic formula, right? So once we have a bunch of linear factors times a quadratic, we've won, right? We know how to factor it. And this is the quadratic that we can actually just factor, right? X minus 3, x minus 5. So we can write this. We've now written this polynomial as factors. We factored that polynomial, and now we just find the zeros. It's going to be minus 2, 3, and 5. minus 2, 3, and 5. And so this is by the factor theorem, right? So we've been using this factor theorem for years. This isn't something new, right? This is just saying once you factor a polynomial, you can use those linear factors to find the zeros of the polynomial, okay? Okay, another theorem. This one's kind of important and pretty useful. The rational zero theorem. And this is probably new. All right, we've got a polynomial here, okay? We have a leading term and a constant. They have to have integer coefficients, okay? So if you have a polynomial with integer coefficients, this is what's true. Every rational zero of f of x has this form, okay? Where p is a factor of the constant term and q is a factor of the leading coefficient, okay? Every rational zero of this polynomial is going to be, the numerator will be factors of this and the denominator will be factors of this. We can ignore everything else in between. All right, so let's list all the possible rational zeros of this polynomial. It's a polynomial. All of the coefficients are integers, so we can use this. All right, they are going to be, let's think about what are the factors of the constant term. Well, 1, 2, and 4. Right, plus or minus 1, plus or minus 2, plus or minus 4. What are the factors of the leading coefficient? Plus or minus 1, plus or minus 2. Right? Now we make a big list and combine all those. Right? We say, okay, if 1 is on top, it could be either of these on the bottom. If 2 is on top, it could be either of these on the bottom. If 4 is on top, it could be either of these on the bottom. Right? So those are all the different possibilities, all the different combinations. And now we just simplify. Right? Well, this is 1, this is 1/2, this is 2, this is 1, this is 4, this is 2. Right? So we just kind of simplify those fractions. So this isn't hard. We just list the factors of the constant term, list the factors of the leading term, write all the combinations, and then simplify those combinations. All right? These are the only possible rational zeros of this polynomial. Why is that helpful? Well, if we want to factor this polynomial, we've got to know somewhere to start. We don't really have any good tools for factoring a fourth degree polynomial. We're going to have to just try some. Right? Our goal is to get from a fourth degree polynomial down to a quadratic. And we've got to have somewhere to start. And this is pretty good. This is 8 possible. There's only 8 possible ones. That's finite, right? We could try 8 different things. Hopefully we won't have to try all 8, but it gives us a place to start if we wanted to start to find all of the factors.